Good day everyone, my name is Kao Tian Chen and I'm from Group 2 and today I will be presenting Lab 1. Our title is Introductions to MATLAB for Communication System. Our primary goal in this lab was to generate fundamental signal and analyze their behavior in both the time and frequency domain using MATLAB. And this is the lab have the three main objectives, and the first is to familiarize ourselves with the MATLAB environments and its core programming syntax. Second, to simulate basic periodic waveforms, specifically sine and square wave. And third, to analyze this signal in both the time and the frequency domain to understand their spectral components. And these are the key parameters we use throughout our script. We set an amplitude of 5 and a signal frequency of 2 kHz. Observe over a 1 milliseconds time window. Crucially, we choose a sampling frequency of 100,000 Hz, and it is 50 times the Nyquist rate, ensuring a highly clean and accurate representations of the continuous signal. Our second signal was a square wave at the same frequency, and in the final task, we introduced noise at a 15 dB SNR. So in task 1, we generated our sinusoids using a single line of code, and then in task 2, we plotted this signal into different way to highlight a key concept. As you can see, the continuous plot on the top show a smooth analog-like waveform. In contrast, the stem plot below display the individual discrete samples. And this serves as an important visual reminder that a digital system actually operates on sample data, not continuous signal. And for task 3, we apply the fast Fourier transform to shift our perspective into a frequency domain. The result is exactly what theory predict. A pure sine wave produces a single sharp impulse at exactly 2 kHz with an amplitude near 5 and absolute silence everywhere else. And this firmly confirms that our signal is a single top sinusoid, emitting all of this energy in concentrated at one single frequency. In task 4, we combine our sine wave with a square wave. This resulting time domain waveform peaks at plus minus 10. But what's far more interesting is the frequency spectrum on the right. Instead of a single peak, we now observe multiple peaks at 2, 6, 10, and 14 kHz. These are the old harmonics introduced by the square wave, and this perfectly validates Fourier's theorems, which state that any periodic wave can be broken down into a sum of sinusoids. And finally, in task 5, we added additive white Gaussian noise (AWGN) at a 15 dB signal to noise ratio. And the red line represents our original green signal, while the gray line shows the noisy version. Even with these visible random fluctuations, the underlying shape of the wave remains clearly recognizable, and this perfectly illustrates the fundamental trade-off in communication system. As noise level increases, signal quality degrades, which eventually leads to error when trying to recover the data. To summarize all our works, we have successfully submitted our MATLAB codes and high-frequency domain probes, a summary of our findings, and a video walkthrough. So overall, this lab provided us with a solid foundations in signal generations, spectral analysis, and noise characteristic. I think that's all from me. Thank you for your attention.